So let me test your knowledge so far, what you have learned about LP model. This is an example of an LP model. Okay, we don't know what the background of this model. I'm just giving you the LP model, the mathematical expression for it, where obviously we are maximizing something. I don't know what that something also. One quick note about that. What's that? This is such that. Okay, so we are saying that let's maximize this such that all these will be met. Okay. Um, so what is this? All right. This is the objective function. All right. What are these? These are the decision variables. What about these? Some of you may answer, well, these are parameters. You told us that the statements are made of symbols and numbers, and the numbers are parameters. You're right. These are numbers. However, these numbers are of very specific interest for us. We are very interested in these for reason that I will talk about it later. But look at this. What are these numbers? They are not any numbers. These are numbers that are multiplying the variables. So we call that what? Usually coefficients, right? And these coefficients are where they are in the objective function. And that's why we call these the objective coefficients. Okay, it's just a name that make our life easier when we are communicating about LP models. All right, then what are these? These are the constraints. Yes, you're right. Then what about that? We did not see this before. When I showed you the LP modeling for the carpenter, I did not add up this. Why this? Because I did not talk about it before. Look, in every LP model, you will always have a set of constraints. This is, by the way, a set of constraints, not one constraint. What are we saying here? We are saying that x1 and x2 and x3 should be greater or equal than 0. For an LP model to work, the decision variables values should be 0 or above. They cannot be negative. Okay, so in fact, this statement represents three constraints, which is x1 greater or equal than 0, x2, and x3 greater or equal than 0. You should always make sure that you specify that non-negativity constraint, we call it. All right, then these you may answer like you did in the objective function. These are parameters. You're right. These are parameters given to us, and this is why they are there. However, these are also parameters of specific interest for us because you see, also these are parameters. Every number is a parameter. Even here, there's a 1 here, right? It's a parameter for us. But these are of also another specific interest for us. These are parameters. Where are they located? In a constraint. Where are they? You see, any constraint, it has a left-hand side, and then you have the sign, and then you have a right-hand side from the sign. So these are simply called the right-hand side values of the constraint. All right, we're going to use these and the objective coefficients later on when we do sensitivity analysis. When we build an NLP model, we have an assumption, or we have a set of assumptions to make. First of all, as I mentioned before, and as the name implies, there's linearity, right? This is why it's called linear programming or linear model. Okay, what are they? This is just to imply that all our functions are of the form y equal ax, all right? You don't see x squared, x cubed divided by x. You don't square root of x, etc. Then divisibility. That means that we allow the solution to have a decimal, as we did in the carpenter problem. Now, sometimes in specific cases, for example, when we are scheduling people on jobs, then the decision variable will be whether to put this guy on this task or not. So in this case, these decision variables cannot be divisible. Or, for example, if your decision variables are number of trucks that have to transport a certain product, these can also not be divisible unless if you are also allowing for less than truckload to be transported. Anyway, For us, for this introductory course, divisibility will be applicable. Then certainty, the parameters given to us, they are certain, otherwise we'll be talking about stochastic programming. All right, and what about here? What about if this assumption is not there? Yes, we have models where we have non-linearity, so these are non-linear programming, right? But we are not learning these here. And finally, the non-negativity, as mentioned in the previous slide. Every model has a set of constraints that set all the decision variables to be 0 and above. So this is called a non-negativity constraint. All right. You need to develop your skills into representing the problem into mathematical expressions. Most probably, or most often, the most challenge comes from the constraints. Okay, how to build the constraints. Why? Because it's not always the restrictions is given to you very clearly. I mean, it cannot be translated very directly to mathematical expressions like the time in the carpenter. Okay, it was very easy for us. However, what if, for example, we are told that the ratio of x1 to x2 and x1 and x2 are decision variables. Ratio of x1 to x2 must be at least 3 to 2. This is not very clear for us. It's not straightforward for us to what to do with it. So do that step by step. And then it becomes very easy for you. And so what's the direct translation of this mathematically? Ratio of x1 to x2, so that's x1 over x2. At least, so greater or equal. Then 3 to 2, so I'm putting here 3 to 2, right? This is the at least, don't forget that. Now, this is not of a final form of constraints. Remember, a constraint or any yes, the constraints are always like that. I have the decision variables on the left-hand side, okay, and then I have a constant on the right-hand side of the sign. So I need to do some manipulation for that. What do? I can multiply, I can cross multiply here, right? So x2, I multiply it by that, and this, I multiply it by this. So here we go. It becomes like this. 2x1 greater or equal than 3x2. Again, it's not yet in the final form. I see a decision variable on the right-hand side. I don't want that, so I'll bring it here. Very easy, right? So I subtract 3x2 from both sides, so I end up with 0 on the right-hand side, and this will be the final form. All right, let me just erase this for you so you can see what did we end up with. All right, now let's take another example where it's also not very straightforward for us. And this example is very generic example, because you see that in most product mix problem where any company has so many products and they want to decide on the best mix. So how many of this, how many of that, because they have shared resources for all these. So if you are given that x1 cannot be more than 20% of the mix, and what's the mix? It consists of x1, x2, and x3. So let's see what the direct representation of that or translation of that mathematically. x1, so I'll put here x1, cannot be more than, so it should be less or equal, right? So x1 cannot be more than, so that's less or equal, 20%, that's 0.2 of the mix. So x1 plus x2 plus x3. You see the logic? Very nice. Math is very logical, and this is what we do in an NLP model. We create mathematical expressions. Now, this is not enough for us. What I want to do is, I cannot leave it like this. I will multiply 0.2 by each one of these. You learned that in your 5th grade, maybe, I don't know. All right, so let me just erase so that you can see the next step, what we are doing. Okay, so I'm multiplying, as I told you, we are multiplying 0.2 by each one of the elements inside the parentheses. And this is not enough. I want to bring all the decision variables to the left. Okay, everything. So I have here one x1, and I will bring 0.2 to the left. It will be minus 0.2. Okay, so that will be 0.8 x1. And here I will get minus 0.2 there and minus 0.2 there. All right, and we end up with this one. All right, so make sure that you practice how to do these translation of mathematical expressions into mathematical expressions. All right, now we're going to learn how to solve an LP model graphically. All right, so you can see, so we are doing now a graphical LP. So graphical LP meaning the solution is graphical. So before that, let's also practice one more time how to translate what's given to us in words or in tabular form, like in this case, into expressions for an LP model. So we'll build the three components of the LP model. What are we saying here? In fact, here I'm showing you the whole thing in a tabular model method, so that I can make the space less. All right, so what do we have here? We have a company that make two computer types, 1 and 2. Each one has different profit contribution, and each one of them has different requirements for the different resources. So for example, type 1 requires 4 hours of assembly time, and I have here on the second one a maximum of 100 hours assembly time available for these two types. And then the inspection time, I need 2 hours for this and 1 hour for that, and I have 22 hours available for me. And then for storage, I need for both 3 cubic feet for each type, and I have a maximum of 39 cubic feet. And we need to determine the daily production quantities of these two types of computers. Okay, how we do that? We need to build the LP model. So let's do this. So here I'm going to denote my decision variables as x1 and x2. All right. So my objective function is, as we learned before so far, that I want to maximize the profit, right? How do I calculate the profit? Here we go. I multiply the number of computers to make, which is x1. By the way, I have missed here to define for you the decision variable. So let me do that verbally. Okay, so we'll say that you always start by defining your decision variables. I really apologize for not putting it for you here. So let's have it. x1 equal number of is the quantity of computer of type 1 that we're going to make daily. Okay, and x2 is the quantity of computer type 2 that we're going to make daily. So my profit would be 60 times x1 plus 50 times x2, and I'm specifying that I want to maximize that. Now, st, so subject to or such that, whatever you want, you put it between the objective function and the constraint. What's the first constraint? I want to look at the assembly time. I have a maximum, okay, of 100 hours. And how much do I use? I need 4 hours for type 1. So if I make x1 type 1, that means I need 4 times x1. And also I need 10 hours for type 2. So if I make x2, that means 10 times x2. So their sum should be less or equal than 100. Here we go. I strongly advise you here to pause the video and try to do the next two yourself. Okay, so let's do that. The next one will be 2x1 plus 1x2 less or equal than 22. And here you can notice that I'm giving a name for my constraints. Is it necessary? Not necessary. However, it really helps to communicate also with your colleagues or whoever. And third one, it's about the storage space. We need 3 for each one, so 3x1 plus 3x2 should not exceed the maximum quantity that we have, all right, which is here, and we call it the storage space constraint. Are we missing anything? Very good. Yes, we are still missing the non-negativity constraint. Okay, so we have to add here x1, okay, and x2 should be greater or equal than 0. This is the non-negativity constraint.